All right, welcome to the first Entrust Solutions Power Gen webinar. So far, we've announced three parts for the balance of this year, once a month, and we look forward to announcing topics for 2023 shortly. We'll start with some introduction slides, and then we're going to move into the content that you came here to see today. So first off, the topic for today is in this webinar series is power generation. But what we did want to talk about quickly is Entrust Solutions Group and some of the other services that are provided. Entrust Solutions Group provides solutions across many sectors, including distribution and transmission, pipeline, and automation. So moving into TG Advisors, some may know us and some may be hearing of us for the first time today, but TG stands for Turbine Generator Advisors, although over the years, our business has evolved to pretty much any equipment within a power plant. But we're a network of experts that have extensive original equipment manufacturer, utility, and engineering consulting experience. We've developed turbines and generators that are developing worldwide, come up with novel service solutions, and also engineer major unit upgrades. So the reason we exist in the market and continue to grow is that we provide independent advice to owners and operators. We don't sell parts and we don't provide manual outage labor. So strictly technical services and owners rep services. We did join Entrust earlier this year and very excited about that and continue to grow as a result of the acquisition. So here's our last slide on our company here and talking a little bit about some of our services. Pretty much anything that you could need as an owner and operator related to the equipment within the power plant. But specifically, a number of our key services are equipment health assessments, optimizing maintenance and capital, troubleshooting and failure analysis, and specifically today's topic, which is steam and gas turbine blade failure modes and mitigating strategies. When we look at failures, a lot of them do come from blading, given the high stresses and conditions that they're exposed to. So quite a bit of our failure analysis is blade related, and we're going to go through some examples today. We do a fair amount of shop surveillance and owner's rep services and metallurgical work, research and development, and then training and education, what we're doing today. So I'm going to introduce our two presenters today. First one being Matt Scoffone. Matt Scoffone is our technical leader for Turbines. He's been with us since 2015. And over that time, he has worked on a wide range of projects, including equipment redesign and retrofits, return to service after significant failures, root cause analysis, shop surveillance, and life assessments. Prior to TG Advisors, Matt worked for General Electric Corporation in various roles, primarily on the gas turbine design side. Our second presenter is Jason Neville, senior consultant for TG Advisors. Jason joined us this year. Prior to that, he spent over a decade at General Electric, primarily as a gas turbine designer, specifically a blade designer, and also a repair development engineer. So now moving into the webinar, the way things are structured today, we'll start with a quick overview of the design of steam and gas turbine blades. We'll talk through failure modes and mitigating strategies. That's the majority of the content. And then we've got three case studies that we'll hopefully get through all three, time permitting. And lastly, we'll open it up for questions. So if you have questions as we're moving through the content, feel free to type them in the chat box.
All right, thanks, Tom. So we'll jump right in here and get into the blade overview portion of the presentation. One thing that we wanted to kind of address first is the blade nomenclature. That way all folks can follow along during the presentation. We'll quickly talk about unshrouded blades here on the left. We'll start with a tip and work our way down. So obviously you have the blade tip right here. A lot of times these are sacrificial blade tips in case you see rubs into the casing. Moving down, the airfoil is this main flow path body of the blade. It's broken up into the lead-in edge and the trailing edge. And at the bottom of it, you have the root fillet and the platform. Below that, typically you have the shank in a gas turbine blades. Sometimes if it's a compressor blade or steam turbine blade, there is minimal to no shank. On that shank, you have cover plates that kind of seals off the shank cavity. They can be integral or non-integral dependent on the blade. And then, at the very, very bottom, you have the dovetail or the root attachment, as well as the axial retention feature. Shrouded blades, the big difference is that these are usually your more aft blades, and they have obviously the tip shroud there. And on that tip shroud, a lot of times we'll have a Z form for the blades to interlock with each other, as well as hard faces or wear faces where the blades are intended to contact. On some of the larger last stage blades in particular, they have what you call a mid-span damper and a snubber, and that helps to support the blade as it rotates. On the very, very right of the slide, you'll see some attachment designs. The fir tree side entry is predominantly used in gas turbine as well as steam turbine. Some of these other designs you see here are more commonly used for steam turbines. So you see the T-root design that will enter into the wheel tangentially, as well as the finger and pin design, which will enter into the wheel radially. And then lastly, the fir tree and straddle design here. And that again is tangential entry into the wheel. Specifically to gas turbine blades, we want to show a little bit more about the forward stage blades. A lot of the forward stage blades are internally cooled as well as TBC coated. And then they have film coolant across the blade. These particular blades have pressure side bleed, trail and edge coolant. They have TBC coating, and then they have lead and edge shower head holes, as well as radial coolant and a sacrificial tip out towards the top of the blade. There's predominantly two types of coolant that you'll see in these forward stage blades. You'll have what you call radial coolant, where you have holes drilled straight through the blade, or you'll have a cord blade that's part of the original casting, and you'll have serpentine patterns as well as turbulators and pin banks that are all heat transfer features trying to keep that blade cool. Aft stage blades a little bit different. They get taller obviously as they go further back in the turbine. There's two different types of aft stage blades. We'll say there's some that are shrouded and some that are unshrouded. See, the majority of them are in fact shrouded in the gas turbine world. So you can see in that middle picture right there. We talked about it a little bit before, where you had your hard faces and your Z forms that kind of interlock the blades together, as well as a steel rail, which is intended to cut into the honeycomb or the seal material on the casing. The other two types that you'll see here, or other types that you'll see, is freestanding blades. And in those freestanding blades, there'll be large freestanding blades here with no coolant in them. This guy's a Siemens design all the way on the right. And then back over to the left, you'll see freestanding blades that are actually cored. And that's done to help cool the blade as well as to keep the pull load acting on the rotor down.
All right, now we'll talk about compressor blades and then get into some of the more details for steam turbine blades. Compressor blades overall are much simpler in design than your hot gas bath blades, primarily just because of the temperatures that they see. Really, they're overall pretty similar to steam turbine blades, typically machined. The design features they have are much less complicated. That left picture there shows the difference in compressor blade size going forwards to aft for a unit. So you're getting smaller as you increase in pressure and also temperature. For compressor blades, usually the more complicated blades design-wise are those forward stage blades, just due to their sheer size, especially for any 50 hertz machine, since those are just so large physically. As far as design details or changes go with compressor blades, one of the biggest ones is just whether you have a simplified airfoil shape or a 3D aerodynamically optimized airfoil shape, as seen on the right-hand side. So that dictates how complicated the blade is to machine and design as well. Usually you get more of a benefit for that 3D airfoil on those earlier larger stage blades, and then as you get towards the aft end of the compressor, the blades are so small that you get less of a benefit. Steam turbine blades in your HP IP section, so these are going to be shorter. They're going to see a bit higher temperatures. They utilize a few different designs. Everything on this slide here really isn't completely comprehensive. These are just some of the most common designs that you'll see out in units operating today. For the blade tips, there's usually some sort of feature that essentially ties the blades in that stage together. So in the center image there, it shows 3 different designs. Riveted shroud design, so the blades themselves have what we call tenons that are peened over this shroud band, as we refer to it, that groups the blades together, groups of anywhere from usually 4 to 8. The 2 images on the left-hand side of this slide show the peening process as it's being carried out. Then there are integrally shrouded blades. So those are small shrouds that are integral to the blades themselves. They're simply butted together as the blades are installed. That's what's shown on the right-hand image. And there's 2 different types of integrally shrouded blades. They can be twisted and pre-stressed, where the blades are actually pushed together with some force, or just butted up together with during manufacturing, essentially no clearance, or little to no clearance between neighboring blades. But then during operation, as everything expands due to rotation and somewhat temperature, you actually can have small gaps between those shrouds. But the twisted and pre-stressed blades with integral shrouds, those are meant to still have contact during operation. And then the bottom image there, this design's quite a bit more rare. I don't believe it's used all that often anymore, but a continuously riveted shroud where you actually have the shroud bands overlap one another, so that the stage forms, the shrouds and the stage form a complete 360 around the circumference of the rotor, where all the blades are tied together. For these blade designs, there's a few different ways of installing the blades, but the majority of them rely on, when you're doing a circumferential entry blade like these, you need to rely on some sort of locking mechanism. So these are a few of the more common locking mechanisms that are used. On the left hand on the bottom there, either what's referred to as a notch or locking or closing blade. So it's a blade that is pinned, so the last blade that's installed is not actually retained by the rotor itself. It's retained by these pins that transmit the load of that blade to the direct neighbors. You could have a notch block, which is the same thing, just with the airfoil removed. So because the neighboring blades are having to carry the load of this blade that's been pinned, that doesn't actually is not retained by the rotor, you have higher stresses. If you remove the airfoil, you remove some mass, that lowers the stresses on those neighboring blades, and therefore the neighboring steeple section. There's this McGinnis locking screw pattern that we've seen a handful of times and have done some RCA work with. A little less common, certainly. Usually it's notch blades or notch blocks, and then side entry locking for blades that utilize that side entry dovetail shape. LP blades utilize some of those same features with some changes, primarily driven by the size and a little bit by temperature as well. So temperatures are going to be much lower, especially in the later stages of the LP. Temperature might not really be really much of a factor if you've only got, say, 125, 150 degree steam in your last stage. These later stage blades, especially the L-0s, as we refer to the last stage, can be quite large, well over 3 feet in length. They are often still tied together at the tips to help with damping. So there's the three most common methods for tying these larger blades together: welded lashing wires, loosely fitted lacing wire, and then loose damping pins at the blade tips. And then there's also, shown on the left-hand image, mid-span shrouds or mid-span snubbers, as they could be called, to add additional damping in the middle of the airfoil, just because the airfoils are so large. Tying them together at the tips not enough to prevent unwanted vibratory response during operation. For fir tree type blade grooves, there's 3 different types that are used in steam turbine blades, especially on these later stage blades that can be quite large. The straight style, an inclined style, or a curved style. That curved style is often used because of just the sheer size of the airfoil, and then also to increase the area, the contact area between the blade root and the rotor steeple. So if you can increase that contact area, you can reduce the stress that the steeple sees by increasing your A, since stress is a function of force divided by area. And then the bottom image, the curved finger root style, this is also been used on some of these larger later stage blades. So it takes the load and distributes it over multiple pins that are driven through those blade fingers that interlock with corresponding fingers in the rotor, and then the pins themselves are what ends up carrying the load.
So now that we've gone through the overview of the blade basics, we'll jump into some of the failure modes and mitigations strategies that are specific to these types of blades. There's several of them that we're going to go through. Most of them are applicable to both gas turbines and steam turbines, but some of them are specific to one or the other. So we'll talk about is our fatigue, both low cycle and high cycle. We'll talk about creep fatigue and rubs and wears, both foreign object damage and domestic object damage. And lastly, we'll talk about oxidation, corrosion, and erosion. So LCF and thermal mechanical fatigue is cracking that is driven by cycling a turbine on and off, or by like aggressive transient emissions. Typically 10,000 cycles or less is considered to be low cycle fatigue when you look at your SN diagrams. LCF is driven by mechanical stress and strain, as you know, and you get tons of that from your pull load. Any sort of stress concentrations, a lot of times if you have root fillets or tight radii, those are the areas most probable to crack. It's also a function of metal temperature and material capability. Depending on what material you have inside of your unit or engine, it is going to be more prone to cracking. Thermal mechanical fatigue, the big thing there is that it's stress driven by delta T, so large temperature gradients. Typically in a gas turbine, for example, your stress is a combination of mechanical stress and thermal, whereas a steam turbine, it's a little bit more mechanical because you don't have as large of thermal gradients that you would in a gas turbine. The picture in the bottom left-hand corner is there to kind of just highlight what we're talking about. This we'll call it as emission is strain versus time for a typical startup of a turbine and shutdown. So the LCF portions are the most left and the most right because that is the up and down of the start cycle. Ways to really minimize the effect LCF is to cut down on your cycling, your starts and stops. Usually base loaded units will be less worried about LCF than peakers, for example. You can also optimize your start and stop missions to maybe make them a little bit more gradual and have more even heating and cooling. From a design standpoint, you can reduce your KTs, you can reduce your temperatures, or you can improve your materials. There's also other things that you can do, such as peening, that will improve your robustness to LCF, but it won't necessarily eliminate it. In the bottom right-hand corner, we have a picture of a cracked blade. You can see that that crack is jagged in nature. That is a hallmark of LCF. Basically it'll kind of grow at one angle or along a grain boundary, and then it'll stop. And then when you go back and turn your unit on again, it'll start growing in another direction. So usually the jagged cracks are, again, they're indicative of LCF. The other thing that you'll really see when you go start looking underneath the microscope is that the cracked surface or the fracture surface will have what we call beach marks. So each of those individual beach mark will represents one cycle or one on and off. So that's one thing to look for as well. Moving on to high cycle fatigue, which is driven by vibration. When we look at our mission, it is a stress that basically occurs while you're at steady operation, or you could pass through a driver on a startup or a shutdown. Typically, it is considered, HCF is considered 10,000 cycles or more. There's different types of vibrations that may occur. There's synchronous, which is always going to be a multiple of running speed. There's asynchronous as well as subsynchronous. We won't really go into too much detail on the three types. We could be here for a while if we did. HCF in general is a function of your mean stress, your vibratory stress and strain. So your mean stress is going to be, if you look at it, it's going to be that flat line across the middle section of our mission, where your vibratory stress is going to be the blue curve that is cycling up and down. The other thing that it is a function of is metal temperature and material capability. Ways to mitigate the impact of HCF is to minimize your off-design operation. A lot of times when you have these vibratory responses, it's because you are holding or operating someplace other than steady state or design, we'll say. And that kind of goes into our next comment. You want to make sure that you're not positioning your hold speeds on top of drivers. The next thing you can do is maintain equipment in good working order. We've seen it on our end where stuck valves will introduce asynchronous stimulus into the system and cause blade failure. From the design side, you can add improved material. You can add dampen features, so pins, dampers. So you saw the mid-span and the tip shroud dampers. You can mess with those. You can also tune your blades by changing the geometry. And that focuses on changes to the stiffness and to the mass. And then you can also mix frequencies or packet blades together. That's kind of more common on steam turbine, where you'll mix blades at different frequencies together, or grab, we'll say 4 to 8 blades and packet them together. The last two things you can do is mean stress reduction, or you can have driver elimination. For example, one of the big drivers is vane count. So the upstream vane or nozzle count, you can kind of change that to remove that driver completely. And those are things that you can all do in the design phase. It's a little bit harder sometimes to do those retroactively. As far as the synchronous drivers, this table right here is focusing on, hey, what could be a driver or cause a vibratory response. You have vane count, strut count, combustion can count in a gas turbine, and then there's always lower per rev drivers. We'll say anything underneath 6 or 8 per rev. There's a lot of multiples or drivers down in that region, so you try and stay away from those if you can. Asynchronous vibration is often caused by flutter or stall, or some other strong driver that is introduced into the system. And the subsynchronous is more from, we'll say, rubbing or looseness of components, as well as nearby equipment. The one thing that's really indicative of HCF, or when you start looking at a failed component, is the flatness of cracks. A lot of times your crack will be very straight, whereas like we talked about in LCF, it'll be very jagged. The other thing is when you start looking at the micrographs of the surface, you'll see a smooth surface because the surface has kind of rubbed itself smooth. Whereas again, the LCF, you'll see the beach marks. Creep is the next item we'll talk about. It's basically cracking driven by the material slowly yielding over time. The material will stretch and form voids, and then cracks typically will begin to connect those voids as the voids get larger and larger. Creep is a function of mechanical stress and strain, stress concentrations, metal temperature, material capability, and most importantly, time. Creep is something that occurs over time. So it's gonna occur when you're sitting there at steady state, operating at base load. So creep would be something you'd be concerned with if you're a base loaded unit. Maybe not so much if you are a peaking unit. Ways to mitigate creep is through stress reduction, temperature reduction. Temperature reduction is a big one. Temperature has a large effect on creep, and you can do that through cooling, the addition of protective coatings or thermal barrier coatings, as well as dropping your gas temperature. The other thing is material selection and geometry changes. In the bottom right corner, you'll see two pictures. The first one on the left is the typical creep material curve. There's 3 different parts of that curve. There's primary creep, which will occur during we'll say the first handful of hours in a part's life. And then there's the secondary phase. And you can see that's typically very linear and just slowly accumulates over time. And then once it hits a breaking point, you enter into tertiary creep, and that's where creep accumulates quite quickly and it leads to rupture. So you really don't ever want to have a part that ends up in tertiary creep, because that's when you're going to reach failure pretty quickly. And just on the bottom right, the very last picture there is a creep failure, and you can see that one was more of a bulk failure where you lost the whole entire airfoil. The next failure mode is rubs, wear, and clashing. It's damage caused by contact between stationary and rotating components. Obviously, it's a bad idea to have rotating components hit static ones. It's typical on areas of tightest clearances. Those are going to be the areas such as your blade tip to casing interfaces. there's also going to be your nozzle to blade axial interfaces and radial interfaces. Sometimes this can even happen with the rotor portions of the turbine. Say some of these components, particularly the blade tip and the case interfaces, are designed to rub a bit, for sealant purposes. That helps keep your performance up, but most are not. Rubbing can lead to material damage, even heat input. A lot of times when you have two items that are rubbing together, heat will be dissipated into the material, and you'll end up with some level of cracking. Also, at times you can lose any sort of protective coating, and that can kind of make things worse, particularly when a gas turbine blade rubs into a gas turbine shroud. If there's a thermal barrier coating on that shroud, a lot of times it's rubbed away, and you'll end up with additional oxidation, corrosion, and erosion that maybe you weren't planning on having. The big thing that you can do to mitigate against this is to increase clearances or start using sacrificial wear materials. Blades will use steel rails or squealer tips, and then static components such as shrouds, or we'll use abradable or wear coatings that are kind of intended to rubber away as the components come into contact. The other thing that you can do is avoid significant transients. The big thing is that if your gas path is really hot, but your casing is still cold, you can cause severe rubbing. And it's kind of the same thing in the steam turbine. It's important to make sure that everything that's thermally soaked and heats up together to avoid any sort of significant rubs. For our examples, you can see a picture on the left is a gas turbine blade rubbing into a shroud. In that particular picture, it looks like all the coating has been completely worn away. And on the right, you can see compressor clashing damage. That's sometimes common in gas turbine compressors. FOD and DOD is caused by objects entering into the flow path that shouldn't be there. These objects can come external to the turbine, or they can come from internal to the turbine. For example, DOD is if you had a broken piece of hardware or a bolt that came loose that got into the flow path and caused damage to the blades. Foreign object damage is something that's maybe left into the engine or pulled in through the inlet. And these are a little bit more common to gas turbines based on the fact that it's kind of an open system, and it gets opened and closed multiple times throughout its life, where steam turbines are a little bit more closed. Good mitigation for this is inlet screens and filters, keeping equipment in good working order and inspecting it regularly. The other thing is that good maintenance and cleanliness practices, making sure that when units are open up, that folks aren't standing around them or dropping things into the unit. Yeah, and this example is compressor blade FOD. You see that quite a bit, obviously, because the compressor is at the front of the engine. Oxidation is base metal attack due to oxidation in, oxygen in gas stream. This is predominantly, or this is a gas turbine failure mechanism. Obviously, because the temperatures are so high in gas turbines. Oxidation is a function of predominantly metal temperature as well as material capability and time. You won't see it within the first couple hours of operation, but over time, the material will get burned away if it's too hot inside the flow path. There's different types of surface coatings that can be used to protect against oxidation, but they do deplete in time. For example, if you had bond coat underneath the TBC, your bond coat would essentially be protecting the base material from oxidation, but it will deplete over time. And when your bond coat depletes, a lot of times the TBC lets go because the bond coat is not good anymore. And from there, you'll see elevated temperatures. We call those post-spall temperatures, where oxidation will begin to occur rapidly. It typically affects the forward stages in a gas turbine more than the aft stages, and obviously that's because your temperatures are hottest as they're closest to the combustor in those stages. And a lot of times they can, lead to micro cracking and then to macro cracking or breach cavities if there's coolant circuits internal to the blades. So it's something that's very serious. The best way to protect against this is really temperature reduction, material selection, as well as, applying a protective surface coating when necessary. There's multiple different types of coatings out there that will help protect against oxidation. The next mode of failure that we'll talk about is erosion. Erosion is when small particulates or water droplets impinge upon or contact blades and cause roughness and material loss over time. There's two different types. Solid particle erosion, affects gas turbines and steam turbines. In a gas turbine, the solid particles that may contact with the blades are sand, dust, rust flakes. In a steam turbine, it's predominantly rust flakes that come from the boiler. Water droplet erosion is common to steam turbines. It occurs predominantly in the aft stages when the steam quality is below the Wilson line and it begins to condense. The water droplets will impinge on the rotating blades at different angles than the incoming steam and cause damage. Good ways to mitigate this, mitigate SPE, is through inlet filtration, protective coatings. A lot of times you'll see those coatings on compressor blades, and then proper equipment maintenance. Water droplet erosion, best way to mitigate that is maintaining high quality steam, selecting high hardness materials or sacrificial materials. A lot of times there's stellite strips that are used on the leading edge of L0 blades, and there's also good operating practices and to make sure that you don't have too much water in your turbine, and that's obviously minimizing any sort of we'll say water coming from or valves or extraction ports, as well as the condenser. You want to maintain good vacuum there. For corrosion affects both gas turbines and steam turbine. In the corrosion, in the gas turbine, corrosion can impact the compressor, especially in environments that are near oceans because there's a lot of salt in the air. There's also hot corrosion, and that predominantly affects the hot gas path because you have high temperatures. A lot of times it's caused by contaminants in water sources if they're used for emissions control or fuel systems. Some of these elements that will promote hot corrosion are sodium, sulfur, vanadium, and potassium. And when these contaminants get into the system at high temperatures, that's when it will attack the base material. Steam turbine corrosion is a lot of times affects the aft part of the turbine. It happens when steam has poor chemistry and it condensates onto blades and attacks the base material over time. So it's always important to have steam and water in the system with good chemistry. Ways to mitigate against this is for the gas turbine, again, it's materials and use of protective coatings, as well as use of clean fuels. In the steam turbine, similarly, there's certain materials that are more are harder or are less prone to corrosion, we'll say. Maintaining good steam chemistry and other operation practices, maintaining good operation practices. All right. So I think that's it for the failure modes, and we left at least a little bit of time for case studies, so I'll turn it back over to Matt.
All right, thanks, Jason. So this first case study, it's a steam turbine blade that was experiencing root cracking. So these are the failure, or I should say the cracking locations that were identified during inspection of this blade. It's a blade design that I don't believe is operating any longer, but the design itself utilizes fairly common geometry. It's got a fir tree style axial entry root, seen in these images here. The first two are NDE images showing locations of cracking. So there are cracks on the adjacent to the end faces of the blade root that were fairly shallow. That top right image shows it pretty clearly. And then there are also cracks on the concave side or the of the blade root there on the top lug area. You can't really see the crack in this image, but it's called out. The location's called out with that red box. But overall indications were found in multiple areas on these blades during an inspection performed during a major outage, and they were present on multiple blades throughout this stage. So these are freestanding blades for this RCA effort and evaluation. We started out by 3D scanning the geometry for an accurate solid model. So especially in this instance, when we wanted to be able to assess natural frequencies and mode shapes of these blades, having as accurate a model as possible of the airfoil especially is really pretty critical in being able to assess your blade natural frequencies. So the best way to do that, if you don't have the original geometry, since we're not an OEM and we don't make parts, is to 3D scan an actual blade. Then we used a finite element analysis software, ANSYS, which is an OEM standard program used widely throughout the industry to assess stress due to stop-starts and steady state operation. As I mentioned, look at those natural frequencies and mode shapes, and then look at the vibratory stresses as well. We also performed a metallurgical evaluation of the fracture surface through a lab that we partner with, and then reviewed operational and steam chemistry data to look for any clues to anything that might have potentially contributed to the cracking seen here if the unit was operated improperly, and then lastly performed fatigue calculations. So for the mode shape analysis, we looked at the first three modes. These are the most common modes to potentially be excited during blade excitation. Mode 1, so these three modes are always going to be similar for larger freestanding blades. Mode 1 is that first bending mode, mode 2 is the second bending, and then mode 3 is first torsion. Mode 1 in particular, that's basically like your diving board mode. And then mode 3, first torsion, that would be twisting along the kind of the center axis of the airfoil. Mode 2 is bending, I'll call it side to side, more forward and aft versus what you see, the circumferential bending with mode 1. Overall, these blades can be excited by numerous sources within a steam turbine. And then these larger later stage blades are, especially freestanding blades like this one, must be specifically tuned to prevent any vibration issues. Freestanding blades are going to be the most susceptible to vibration problems, so that's why a lot of those design features that we discussed earlier are usually implemented, whether it's some sort of tip shroud arrangement or just something to tie the blade tips together, and potentially those something to tie the mid spans of the blades together as well. In steam turbines in particular, high back pressure levels are one such source of potential excitation for L-0 blades, your last stage blades. For this blade design in particular, the steady state stress results, or the stress results that, or the stresses seen just purely from startup and shutdown, are shown in the plots here. So that top left image, we had good agreement with the stress results for this blade for where we were seeing cracking on that upper lug on the concave side of the blade. However, the the edge cracks that we're also seeing, we weren't seeing stresses or high stresses in those areas just from normal operation. So the top right two images, those two pictures do not use the same scale as one another. So the left image there is a similar scale to, or I should say the middle image on this slide is a similar scale to the left image on this slide. The right image, that's got the scale modified to just better show stress magnitudes in the area in question here. So ultimately, we found that steady state stresses calculated through the FEA, they're highest in the same area that indications were found on the airfoil suction side, the convex side. I think I said concave side earlier. That was just a mispronunciation. It was convex side or the suction side of the blade dovetail. So this helps us kind of ground our model. We have excellent correlation between the FEA and the experience, but then we also need to still find out why are there cracks in the end faces. The indications on that convex side in those areas typically are low cycle fatigue related, but they can also be have a high cycle fatigue interaction too. So it's important to understand the duty cycle and operating profile of the unit. Because those steady state stresses were low in the areas with end face cracking, though, we had to figure out what could be driving those cracks. And so that brings us back to vibratory stresses and our natural frequency and mode shape analysis. So taking the vibration that the blade sees in the mode 1 first bending mode, we were able to force the blade model to the blade tip basically to displace according to vibration that we would see in this mode, and then assess the stress impact on the blade root. And what we saw was that for this first bending mode, when the blade's excited, having the blade tip displace actually increases stress, specifically in the areas adjacent to the end face that we were seeing cracking. So great correlation between stress due to first mode vibration and the low case of the end face cracks. So ultimately, the cracks for this blade were a function of LCF and HCF as well. And it's also important to note that fatigue damage is cumulative or additive. So you could have cracking initiated by LCF and then propagated by HCF, or vice versa, or potentially a combination of the two. The second case study here is looking at compressor blade failure. So for this compressor blade failure that we investigated, it was an aeroderivative gas turbine. It's portable, transported to remote locations. The high pressure compressor section has what's called variable inlet guide vanes, followed by 7 stages of variable stator vanes. So all of those vanes can rotate depending on the speed of the engine. The unit tripped during operation due to a compressor stall event, and a bore scope conducted on site showed extensive damage throughout stages 1 to 12, and then stages 13 to 15 were not accessible due to blocked bore scope ports. But that bore scope report noted material likely detached from stage 2, as that stage seemed to have the greatest damage. Part of this RCA included evaluating prior reports just to see if there was any trends or anything to potentially warn of an impending issue. The only relevant finding from those prior borescope reports was that deposits and salt were noted in the high pressure compressor, and the compressor external was noted as being dirty in one of the reports in particular. There was a prior recommendation made to perform an external water wash at the next opportunity to prevent more buildup and potential variable stator vane system issues. Key inspection findings from our on-site evaluation. The stage 0 vane 9 had a broken and partially missing lever arm. So it's the middle and bottom left images. The bottom left one shows the missing linkage, and then the middle image shows the as found position of that vane. So that one was off schedule, was not operating since it had no longer had a lever arm to drive it. Stage 2 vanes A few of them had bent lever arms. There was one missing row 2 blade where broken off below the platform. So the airfoil had completely liberated. The dovetail was still in the rotor. And then overall the damage started at the row 1 blade trailing edges. So that off schedule stage 0 vane is a critical finding in this case. Every time you're rotating blades past that point, the flow they're seeing changes, and so they're seeing a differing impulse once every revolution. So we call that a 1 per rev driver to drive blade vibration. So ultimately, the root cause, once we conducted metallurgical testing as well, ended up actually being fretting in conjunction with high cycle fatigue. So our initial thought when we saw that off schedules variable stator vane was just high cycle fatigue. But in this instance, these blades are a titanium alloy that's pretty commonly used in aeroderivatives. That titanium, 6 aluminum, 4 vanadium. That's highly susceptible to fretting on the dovetail surfaces in particular. So this alloy, the titanium alloys in general, tend to be more negatively impacted by fretting than steel alloys. Fretting being the relative motion between the blade dovetail surfaces and the slots that they are retained within in the rotor. So that image on the top right, it's a greatly magnified image of the blade dovetail contact surface. So you can see the really rough appearance, especially the edge of the material there, kind of right in the center of the image. The bottom right image, that's 3 of the blades from this engine. So those kind of shinier areas that you could see with the red arrows pointing to them, those were the areas of greatest fretting. The fretting was worst in an area on the leading edge suction side corner of these dovetails, and one of the most important aspects was that it was consistent on all the blades, provided a TGA. So being that this alloy is highly susceptible to fretting and the reduced material properties as a result of fretting, the OEMs are aware of this. They apply protective coatings on these dovetail surfaces to try and minimize the impact of fretting if any sort of relative motion does occur. In normal operation, that coating should be enough to allow these blades to last for an appropriate period of time or for their design life. But when you have something such as that significantly off schedule stator vane, that's going to greatly increase the vibration these blades see, and that can lead to that coating actually being worn away and then the base metal being exposed. And once that starts fretting, then your material properties are significantly reduced, and that's when you can get crack initiation and ultimately failure. So overall, it was determined that the blade failed from fretting, promoting crack initiation, and then high cycle fatigue driving propagation. So that bottom image there actually showed 3 different initiation sites for the cracking, and the cracks slowly grew, or I should say 3 different initiation sites on one side and then another initiation site on the opposite side of the blade. That shiny area is at the top of the image, the area of the worst fretting, and then the cracks ultimately grew inward towards the center of the dovetail from both sides of the blade until the airfoil just separated.
Man, I think we'll wrap it up right there and see if we have any questions. So I think there's a way to go ahead and ask questions through the teams here. So feel free to publish them. It looks like we had one question from Andrew Lowry about failures due to torsional vibration interaction with electrical networks. Does this show up as HCF? Matt, do you want to maybe explain your response a little bit?
Yeah, sure. So torsional interaction, or I should say torsional vibration, that's where the generator actually becomes the shaker. Basically, your generator is driving a torsional vibration of the rotor train. If you have long enough later stage blades in your LP section, those blades themselves have enough mass that they can respond from the torsional vibration of the rotor train. But usually it's just your last stage or maybe your last two stages. It'd be pretty rare that you'd see blades more towards the inlet section of your LP, or certainly any blades in an HP or IP respond. They're just not big enough. They don't have enough mass. But in particular for nuclear units, since the units operate at 1800 RPM versus 3600 for 60 Hertz market, your blade sizes end up being much larger, and so that's where you might get multiple blade stages that actually could respond to a torsional vibration. Overall, though, it's really going to come down to, does the rotor train have natural frequencies modes that are close to that double line frequency, and then are your blades large enough that they could actually be their vibration response could be, or they could be excited due to that torsional vibration. Do the blades themselves have enough mass? The crack would then be high cycle fatigue due to resonance driven by the generator.
Matt, so it looks like we had a request to go through the last case study super quick if possible. So maybe if you can give a 2-minute summary of L0 blade erosion. I think that's it's pretty common, so I'm sure people have seen that before.
Sure. Yeah, let's go to that first slide because I think this will be a good summary slide. So later stage blades, especially your last stages, highly susceptible to erosion. So any blade that sees wet steam is going to be susceptible to erosion, but your last stages in particular, they've got longer blade airfoil lengths, so your blade tip velocities are higher. You got more energy being dumped into the blade when water droplets hit it, so it peels off or erodes the edges more quickly as a result. During normal operation, it's not as much of an issue. It's really worse during off design conditions, so startup, shutdown, part load, when condenser pressure is high. So if you got poor vacuum, those off design conditions, you can actually get steam recirculation. So as shown in that image at the bottom there, during low load and in particular no load, you can actually get the steam flow start to recirculate. And so the most common place for erosion is going to be the leading edge of your blade, especially towards the tip, maybe like the top third of the airfoil. But if you spend a lot of time at low or no load, you could have erosion actually on the trailing edge of your blade. That's usually down more towards the blade root. That trailing edge erosion is more concerning. Since you've got higher stresses in that area, there's more material outboard of it pulling on that area, basically. There's a number of ways to try and mitigate this. Usually it involves hardening the leading edges with something like stellite shields or inductive flame or laser hardening. But overall, minimizing off-design operation. If you've got significant erosion, is always a good idea. Establish good vacuum as soon as possible during startup, and maintain it as long as possible during shutdown. Hood sprays can also drive erosion, so operate any exhaust hood spray systems if they're present infrequently as possible, and inspect frequently. Erosion is kind of a tough one. So I'd say, I guess the most important thing overall is that once your blade starts eroding, you don't want to take any measures to smooth it. You want to leave it alone. The erosion rates will actually slow over time. It's hard to judge erosion purely based from photos, especially any sort of zoomed up photo. since a photo, the closer you are to the blade surface, the worse it's going to look. Really, it's more a function of kind of how much mass has the blade lost. So there's a few different concerns. Obviously, erosion, that's a very rough surface, so there's concerns over cracks starting or initiating from the eroded area. But then you also could potentially lose enough mass that you also change the mass of your airfoil and change the natural frequency of the blade. So a blade that was well designed could then potentially lose enough mass to start having excitation and vibration problems.
Matt, I think you covered that one pretty well. I think that was all the questions that we actually had, as well as I think we're at time. So just a big thank you to everyone who joined. We will publish this recording and distribute it accordingly. So thanks very much for joining us, and we hope that you guys have a good rest of your day. And please tune in to the upcoming training and webinars that we have. The big one that's going to be next. There's going to be an operator training in Newark, Delaware, as well as our next webinar will be on 11/17. So please feel free to go ahead and join in, and we'll send out reminders as well. Thanks so much.